All right, I know people are still trickling in, but we're going to get started. First of all, welcome to Identity at Scale. My name is Greg Smith, and I'm the track lead for this series of sessions. We have some very interesting sessions today. We'll be hearing about unique solutions for very large-scale identity implementations. You are going to notice a recurring theme across all three sessions, talking about automation, avoiding downtime, adapting to cloud hosting models, and staying cost-effective. So let's get started. Based in Colorado, Kevin Shanley is an Associate Vice President and leads the Access Entitlements and API Service teams at Cyberinc. Kevin has been working in the identity and access management field for 20 years and is focused on complex, high-volume projects with clients across more than 30 countries and servicing hundreds of millions of end users. Kevin, it's all yours.
Hi, and welcome to the next-gen cloud architecture discussion. We're making the whole digital transformation secure and cost-effective. I was going to start by introducing myself, but looks like I've already been introduced. Oh, got to stay close to the mic. So I guess the one thing that wasn't in there was I'm kind of also a hipster geek who's bicycling and PC gaming outside of a normal IAM time. But I wanted to start this off with just a quick background of how I actually got this topic. And it goes back about a year and a half, 2 years. I was at one of these conferences, and I was called into a TV interview to talk, I guess, as an industry practitioner, expert practitioner, and talk about, get some sound bites on identity and access management in the space overall. So they hit me with this question. What is the digital transformation? Or what is the digital transformation to you? And I didn't have an answer. I'm a low-level techie guy. I'm constantly focused on writing code, getting solutions out. And some of these higher-level marketing terms maybe just get a little bit beyond me. But it bothered me. It also bothered me it was all on film, and that's never as much fun. But as time was going by in this past year and a half or so, I kept going out to customer sites, and I travel a lot. I visit all these different large enterprises, large government institutions to provide some services on IAM. And I kept hearing this same theme over and over and over. And it was, Kevin, we started moving things into the cloud, and this whole thing is looking like it's going to be a lot more expensive than our current solution. And so these two things kind of kept coming together with me. Why is this happening? Why are large enterprises, why can't they make this stuff work? So I just like to go through as a part of this, break down how a little bit of a container virtual machine primer, how this stuff actually performs, pull that back together with some automation information, the infrastructure as code, and regroup into a digital transformation and see what real cost savings actually look like and how we can get to it. Quick one, what is Docker? I think most of you actually know what Docker is. You're pretty into the technical low levels of this stuff, so I won't beat a dead horse. But Docker is essentially the tools and platform to manage the life cycle of containers. With this, Docker's trying to sort of revolutionize the IT infrastructure space in the same way that standardized shipping containers revolutionized the shipping industry. But let's see how these models actually compare to each other. So, first up is just our native machine model. It's the one that everyone's familiar with. It's hardware. On top of your hardware, you're running an operating system. And on top of that, you're running some apps and libraries. This is always going to be the best performing model. And as we move forward to a virtual machine model, this is also one that's going to be pretty well familiar to a lot of you. It's essentially the same type of a model, where we have hardware at the bottom. But now, what some of the engineers then looked at and said, hey, wouldn't it be nice if on one piece of hardware we could run a lot of virtual machines? And to make that, to enable that, they had this hardware supervisor called a hypervisor. And it has to translate all those calls from these various different operating systems. Now, while it's great, it allows us to maintain this paradigm of physical servers turning into virtual servers. We have exactly the same type of logical architecture. There's a cost, and the cost is that hypervisor, that extra layer which can really affect your performance. And finally, it's the container model. And this is the one that tends to be a bit newer to most people, where we said, hey, operating systems were always built to manage hardware. So why don't we let them do that? Why don't we keep that operating system on the bottom layer? And then on top of this, we'll have a much, much thinner layer where we have a bit of a virtual file system driver, we have some other virtual components, but it's nowhere near the level of translation that needs to happen for a hypervisor. So what Docker's going to do is it's going to take a single operating system kernel and provide isolation and resource control. And how does this stuff actually perform? So we ran a whole bunch of different load tests on identical hardware, but running different types of things, like how you would actually run, not just running stuff up in the cloud, but actually taking a physical server, getting native benchmarks, then loading in a type 1 virtual machine hypervisor, and getting some performance benchmarks along that. Likewise, a type 2 VM and Docker. I think you can read that pretty well. But essentially we have with this native model, that's 100%. It's as good as our performance is ever going to be, and it's our reference point. Now the type 1 VM, that's a hardware hypervisor. It's like VMware ESX server, Linux KVM, and that performs actually pretty darn well. You get, you take a performance hit, but that's maybe not the entire story. And we start to see more of the effect with the type 2 hypervisor. And that's maybe the one that most of you are actually familiar with directly, which would be like VMware Workstation. And in fact, the type 2 hypervisor in our test performed so badly, we extrapolated these results and we ran them on Mac, Linux, Windows. We ran on different hardware rerunning it, and we were consistently getting like 400% performance degradation. And that's just, a type 2 VM has an operating system, and then that kernel level hypervisor and another operating system. So it's got a whole extra layer, and you just get killed. But finally is that Docker data point, and that is truly near native performance. And when you see Docker's architecture, you start to see why. It's because it's doing really very little in terms of the isolation component. It has nowhere near as much to do. So, whenever I'm trying to make a point, I think to myself, well, so what? Maybe Docker performs a little bit better. Who really cares? The virtual machine provides better isolation between these components. I can maintain my same my server paradigm and hardware architecture. What's the point? Well, let's see how this actually applies. Let's go ahead and build ourselves a server. And with the server, we'll take one new generation CPU that has 64 processing threads, and then let's take this one CPU server and put some virtual machines on it. And that's essentially what this is going to look like. This is going to be a hardware hypervisor, and then 16 operating systems running on top of that, and your app layer. Now, does anyone see any potential issues or overhead associated with this model? And before you even load the apps, you've got 16 different operating systems with low-level processes, high-priority calls, all going into one physical CPU. And this is kind of our simplest model. This is only a one CPU server. And this is using really today's hardware. So you can quickly see how this can get out of control, and how what might have been sort of a 10% or 15% performance hit could actually turn into a heck of a lot more as you start multiplying and multiplying this model. And I didn't even mention the elephant in the room, which is those 16 operating systems, they need management. Some sysadmins got to get in there, install them, put on the updates, manage the system accounts, get the auditors in there. There's a lot of administrative overhead on top of this. And this is how it looks with Docker, where essentially we've gone back to this 16 apps, one operating system, and all of those operating at near native performance. And really, this brings it back to containers. It gives us this platform, and it rids ourselves not just of the CPU overhead of all those operating systems, but the management overhead. And that's really where a lot of this transformation takes place. It was really a wonderful thing in the early 2000s when you could go to a data center and say, hey, you see those 16 servers over there? I can put them all on one server. Oops. I could put them all on one server. And that's a really powerful argument. And that's what we've seen over the past 15 years, is that's been the direction. But now we're starting to see that model kind of fall apart. Because as we can put more and more onto that hardware, as we can really reuse it, that cost model starts to break down. So how do you manage it? And I just wanted to do a couple of quick slides on this because I get asked this at really every customer site we go to, where they're asking about the next-gen technologies. Hey, what's Docker? What tools are your other customers using? And this gets into the infrastructure as code realm. What this tries to do, it gets us away from this physical paradigm of, I'm an app owner, and I need to request a couple of servers and DNS and firewalls be open for a given app. So I'll fill out an IT request ticket, and maybe some admin will plug something into the network. And that's slowly been going away, and now we're moving more to virtual machines. But as this stuff moves to the cloud, you no longer need to do that. So what are the automation tools that people really like to use so that when I request that, we auto-generate the virtual machine, we auto-generate the container, we update DNS with those entries, auto-update the firewalls. And these are some of the names that come up over and over and over. So when I'm asked this question, Chef is the technology that I've seen at most of our large customers. I'm not plugging Chef or anything. This is just the one that I tend to see over and over and over. It's a server node-based architecture. They have these cookbooks and things. And likewise, I went out to my team and said, when you get called into a customer site, what are the technologies you like to have them have? What's the stuff you like to work with as techies? And the result from that was resoundingly, everyone came back and said, yeah, Ansible. It's easy, it's agentless, just kind of works. I think it's probably more expensive. I don't look at that stuff, but. So yeah, due to time, I have to quickly move through a lot of these things, but I'm good? Okay. I guess bringing it back to, why do we need this digital transformation? Why? Really, what is it about? Okay, it's some concept of elastic computing, something around this. Well, when I go out to these customer sites and they say, hey, here's my data center, and let's go ahead and put all this stuff out on the cloud. And they start to do it. And they forklift their site, or what I would call shoehorning their site into the cloud. And they'll basically look at their site and say, okay, I've got a virtual machine here on my local data center. I'm going to put a virtual machine in the cloud. Boom, 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 boom. And through that, they just essentially start recreating their actual infrastructure in the cloud. And why does this fail? It really comes down to the fact that you didn't change anything. The management overhead of all those operating systems you had on your local data center, you still have the management of all those operating systems in the cloud. Maybe you thought you were going to get some cost savings because going into the cloud, they're going to have an economy of scale that we don't have. Well, for most of the customers that I work with, they have 100,000 servers. They have economy of scale. And I was actually having a conversation a while back where we were looking at putting a large bank into the cloud. And we realized we were going to triple the size of the cloud service overnight if we added our customers into theirs. And that's because large companies, they existed around an economy of scale long before the cloud existed. And that calculation is starting to change, but you can't expect to actually necessarily run away with stuff and get a lot of cost out of it. So one of those last things is maybe your apps could scale elastically, but or you probably didn't force them to scale elastically when you put them in the cloud, so you could never turn them off. So I wanted to take a couple of example use cases with my applications, and it's my tale of two apps where I look at ping access and ping federate, and they present kind of two different models, and you may get some lessons learned for how you build your own apps or how you try to scale elastically yourself. So first up is ping access. Ping access is a modern app built just in the past couple of years, and it's built to work elastically and work in a cloud. Conversely, ping federate's been around over 15 years, and it's got all sorts of other messy things. It's got these state cache clusters that need to be synchronized between nodes, all sorts of LDAP and database connections, and it's got some legacy architecture that you need to be aware of. So let's look at that ping access setup. Those things in dark blue, that's the one engine in the admin. Those will be the nodes we'll keep up all the time, but the rest of it can be elastic. And the really neat thing about this model is ping access supports clustering, but there are very few features that actually require it. And in fact, there's only maybe one feature that if you really needed it, you'd have to turn it on. And generally, for our customers, we don't turn on ping access clustering for anyone. which means that you have a 100% linear scalable model of, as you fire up another node, you get exactly 100% of a new node's performance. It's really quite a neat model. The other side of it is, at the bottom of those ping access engines, you'll see a little H2 flat file database. The neat thing there, and this kind of, it goes for what I'll say for all mutable data on an elastic model. When I bootstrap, I fire up a new instance of ping access. One of the first things it's going to do is contact the admin console. And it's going to download all of its policies. It's going to download all of its SSL certificates, all that changing data that may have updated since I was last turned on. So the neat thing there is it just kind of works out of the box. There's very little to script. You can fire up those models, and come nighttime, you start maybe an employee workplace scenario. Your employees are going home. Let's start turning off the servers. So from a ping federate standpoint, things get a little bit more interesting. And we have now these database connections, LDAP connections. Those potentially present a problem, but that's not a real problem. The real problem are those little arrows that go between the clusters. As I add more nodes to my cluster caches, they start to get exponentially less efficient because every new node I add needs to be synced with all other nodes. And this presents kind of a problem because as I start elastically scaling up, I'm going to hit a point where I actually start scaling up and my site performance actually starts going down. So really, this type of scenario can work for a small site. Or I should say a small mid-sized site. If you're going to need more than this in an elastic scenario, then we can look at our next model. One of the other things that kind of comes up is, whereas ping access is a pull model, when you fire up a new instance, it's aware that it needs to download the latest information and get up and running. Ping federate is not. When you fire up that instance, it's going to run with whatever configurations it knew about last time. So you need to force some sort of a cluster push out to all this stuff. Makes it a little more manual intensive, but it's also things to think about in your own models for your own applications. And what they support for ping federate going into a much larger environment is, hey, what if we could take those cluster caches and separate them out? And it's supported. You can put this out on state servers and have those running in the background. They can actually be relatively small engines as well, because where you need to scale in PingFed is your CPU usage. You're signing and encrypting all these SAML messages, signing and encrypting OAuth tokens, having all these SSL connections coming in. It's very CPU intensive. So we want to separate out that type of behavior. And we end up with a logical architecture, something like this, where I would never deploy something like this where you're on one hardware machine, but essentially we can take an environment that has a scalability of 8 servers and at nighttime scale it down just to 2. So if we look at that model, and if we shut down those idle servers at, say, an average of 12 hours at night, and there are lots of different scalability elastic models. If we look at a workplace scenario where your workers go home, middle of the night, you only need to run 1 server, then you can actually shut things down for 12 hours. Have just sort of a minimal footprint running. And if we have a cost per server of, say, $1,000 per server per year, and we're able to shut them down for half that time, well, that's going to end up saving us $500 per server per year. Doesn't sound like much, but then when you're one of these organizations that has 10, 50, 100,000 servers, you start talking real money, where it's $5 to $50 million in savings. And that's kind of a standard elastic scenario, and there are all kinds of different ones where I'm going to scale up with my swarm cluster based on load, or we have our dream scenarios where these were always the best elastic use cases of you have an IRS tax office or health insurance company where 90+% of your load comes in the course of like 1 month time period. So we already know when the load's coming. It's coming in the month of December or the month of April. And that really allows you to quite efficiently use your resources. So finally, the only way you can save money is by turning this stuff off. And it does mean sometimes fundamental changes in how you're setting up applications. You need to make them elastic aware, which means that you need to essentially fundamentally change how they're using things. Engines can scale very well. Clusters and caches like that do not. As you scale caches out across more and more nodes, your cache hit ratios start to plummet. And you just need to think about that for your application architecture. And this last point, don't underestimate it. It takes a long, long time to operationalize a lot of these concepts. When we were going through a lot of this testing and figuring out, isolating our various cluster consoles, isolating our various container instances, we ran into all sorts of problems. You know, the performance tools you're used to using in an operating system, that's not necessarily what you're going to use when it's now in Docker. Isolation that you once enjoyed in a virtual machine, it's not necessarily going to be there from a Docker type of setup. All right, so we can open this up for questions. And I also just wanted to quickly mention, we looked at potentially putting together content like this for a master class. This is actually, there was a much, much, much longer setup where we would set up like a swarm cluster with ping access, ping fed, be scaling stuff up, and have all this stuff on an open source repository.
Thank you, Kevin, and perfect on time. So we do have 5 minutes for questions and answers. If you would like to ask Kevin a question, please put your hand up. This session is being recorded. I'd like to bring you a microphone so everybody can hear, and also posterity will be able to hear on the YouTube video. So, questions?
Thank you. So, my question is, operating system does many nice things, say like memory protection. So like if any application is creating trouble, shut down that application or isolate that application. Then virus protection, then access control, all these things. So Docker takes care of all of these?
That's correct. So what a Docker container will essentially add, it adds a concept of a virtual file system. So it can actually make the file system for a given container disappear from everything else. From the memory standpoint or memory protection or those ring zero operations from a machine standpoint, what it essentially does is to your given process ID, it attaches a tag, which from an operating system perspective, it's going just like it would separate different applications. Using that tag, it's essentially isolating your containers from each other, which potentially, okay. I was just going to say, it does potentially take away some of your troubleshooting tools. So, you know, if I were to not have Docker and run 16 different apps just in different directories, I don't necessarily have that isolation, but I have access to all those native OS tools where I can inspect memory and do all of that stuff. And Docker abstracts some of that stuff.
Yeah, so two-part. In the WAM implementation that you put up there, how are you handling state across the expansion, the elastic portions of it? And are you using Swarm or Docker Data Center for the pieces of the Docker environment for those pieces?
So for those tests, we used a Swarm cluster. We wanted to run everything on our own hardware, you know, with kind of the latest and greatest tools, make sure that we're comparing a lot of apples to apples. And, oh shoot, I've lost the first part of your question now. State. So state across your the ping access engines. Ping access supports clustering both for token mediation and for proxy rate limiting. Now, unless you're using either of those functions, you're basically never going to turn on clustering. And even if you are using token mediation, I still generally tell people not to turn on clustering because the overhead of trying to propagate those sessions across cluster nodes, it's not necessarily going to make itself worthwhile. From the ping fed standpoint, that's where we want to separate things out into state servers. Like if you really want to scale up beyond 4 servers, you need to think about separating that bit out. It does need to then generally stay on, but those engine nodes, when you do fire up a new engine node, you have a couple of options. You could manually copy the configurations down in there, or you call the API to push the cluster config, but then it pushes out to all nodes. So it's more to think about, and if you're designing your own app, a pool model generally is a lot easier to work with.
Yeah, for the ping federate files that are not replicated when you when you replicate your state to the cluster, like the stuff in your server default deploy directory and your templates, do you find you're coding those specifically into a Docker image, or are you running a script to pull them from like an S3 bucket or something?
Yeah, this really gets into the discussion of other mutable data. So, and I guess the question, if I got that, it's about things like login templates. I generally like to run a lot of that stuff on a different, connected drive. Likewise, if you do have, we've also done some funny stuff where we put on our admin node additional bits of information that we want to be able to sync with the cluster when it fires up, or with those engine nodes when they fire up.
We have time for one more question over here.
Hi. How do you manage to mitigate the problems that could happen when you have shared services, let's say on AWS, and you have a buffer overrun and memory space leaks into another process? So when you have something like Docker, it's possible you could create a buffer overrun or underrun in a container and then read data from a container that's completely separate from this one, from another company. Have you ever encountered that?
I have not encountered that, but it's certainly possible. It's as with any of these container isolation models, Docker does not give you the same containment as a virtual machine. A VM, it really gets quite well self-contained by it. So there's some potential risk added to that. The other part of it is, in this presentation, I sort of showed this model where we have one piece of hardware and a whole bunch of different services running on it. You would never run this like this. All these nodes should be running on different bits of hardware, and that's actually a major operational hurdle for a lot of customers, where they go out and they start co-locating a lot of like-for-like services. And I guess in one of the most recent releases of Docker, it allows you to much more better separate nodes. But by default, this is how it might even deploy. And then that hardware server dies and your entire site goes down. So yeah, you do have to be wary of what you're going to deploy where. Generally for a Java app, I don't think you're going to run into that type of a thing. If you're running lower level C-based apps, and that might even be using libraries out of the lower level OS, that type of thing is much more likely to happen, and I would just put some rules around it and constrain it separately.
All right, Kevin, thank you very much. And to everybody in the audience, thank you for your participation today. The next session actually starts in 5 minutes. That is going to be right here, or if you have a session in another place, you may need to take a bit of a run to get there. But before you go, if you haven't already downloaded the CIS 2017 app, please do so. And please go in and fill out session surveys. We'd like to know how much you appreciated the session, and if you have suggestions for improvements in the future and new sessions you want to hear from. So thank you all for coming.